Okay, so I'm just gonna go over this question here on a balanced bridge circuit. So what's happening here is, again, we use bridge circuits, or they use bridge circuits, Wheatstone bridge circuits, to try to um, measure very precisely the resistance of unknown resistive value. Um, that's where they use them. And what they do is they use this galvanometer, which is measuring potential difference, and they have it bridged across in the middle of two sets of resistors that are in parallel. So this point and this point here. And if it measures 0, that means there's no potential difference between that point and that point. And therefore, the voltage drop across this resistor here would have to be equal. And the voltage drop across that point and that point here have to be equal. Okay, we don't know what the voltage is in this particular case, but it doesn't really matter as long as we know that relationship. And so I'm just going to show you here that the ratio here, if our 25 and 105 ohm resistors that are right on top of each other, that ratio of resistance has to equal this ratio of resistance here. And likewise, another way of thinking about it is that because we know that there's a proportional relationship between resistance and voltage, well, let's say this was like 100 volts or something like that, we would know that on as well, the voltage across these two resistors here would have to equal 100 volts. And we know that the voltage on the resistor that is 25 ohms, there's going to be less of a drop than there is on the 60 ohm resistor. In fact, we know exactly how much it's going to be. If we took 60 divided by 25, that's going to give us 2.4. And so we know that the voltage across the 60 ohm resistor would have to be exactly 2.4 times more than the 25 ohm resistor. Okay, so if that's true, then we know that that relationship has to be the same down here. We need to have the exact same voltage drop, even though we're dealing with larger resistors, doesn't matter. The relationship has to be the same. The Rx here has to be 2.4 times greater than 105 there. And that is going to allow the voltage drop to be the same from Rx and 60 as well as 105 and 25. Okay, so we can express that in a formula, or if you want to rationalize it, again, 60 divided by 25 equals 2.4. That's our multiplier. And now we can just multiply 105 by 2.4, because we know that, again, this resistor has to be 2.4 times greater than 105, and that's going to give us 252 ohms. If you want to express it in ratio form, in a formula, you could do it like so, 25 over 60 equals, and we need to make sure that we get the resistor right below 25 there, in line with the 25 there. So that would be 105 equals Rx. Now, we could solve for Rx, and you're going to come up with 252. Now, you might notice as well, especially if you're familiar with transposing and ratio relationships, if we invert both of these fractions here and go 60, 25, and Rx over 105, that's the exact same relationship. They're still going to be equal because we flipped both of them. And if you wanted to do that transposing, well, if we brought the 60 up to the top of that one and the 105 down to that one, and the Rx up to that side and the 25 down to that side, we end up with this formula here. Down here. Likewise, as I sort of alluded to at the beginning, we can also express it as this ratio here, this relationship. This ratio has to be the same as that ratio there. So that would be expressed as 25 over 105 equals 60 over Rx. And you might notice that all we're doing there is flipping these two values here. So the Rx ends at the bottom of the 60 like we have here, and the 25 ends up at the top of 105, which we have here. So it's all the exact same ratio. And now if we solve for Rx in this formula, or Rx in this formula, or Rx in that formula, it doesn't matter at all. You're still going to end up with 252 ohms. But again, the way I like to think about it is, going back to the beginning here, that this here, if we figure out the multiplier, again, 60 is 2.4 times greater than 25 if we divide 60 by 25, 2.4 times. And so all we got to do is go 2.4 times 105, and we end up with 252 ohms. And that's our answer. That would make a balanced circuit.